So my name is Sian, and I'm going to be talking about a system that we've developed for contextually aware lexical simplification. And in order to actually explain what lexical simplification is, I'm going to start with a definition of text simplification. So text simplification refers to the process of reducing the complexity of text whilst preserving both the meaning and grammaticality of the original piece of text. And there are a wide variety of processes you can apply to text in order to simplify it. Broadly speaking, these group into three different categories. So the first category is conceptual simplification. And this is where you would aim to actually simplify concepts within a piece of text. So an example might be if you saw the sentence, Brexit means Brexit. If you aren't familiar with what the concept of Brexit actually is, you may need some help actually understanding what that means. And one of the ways that you can do that automatically is maybe by having a definition of what Brexit actually means. The second type are lexical simplifications, so this is also known as word simplification, and this is where you might want to identify words within a piece of text that are complex and then aim to simplify those. So in this example, we see treacherous has been identified as a complex word. You might want to replace that with dangerous instead. And then the final type are syntactic simplifications. So this is where you're aiming to reduce the complexity of the syntax or the structure of sentences. And one of the ways that you might do this is something called sentence splitting, where you aim to take long, complex sentences and split them into smaller sentences instead. So as you can tell from the title, our specific system deals only with lexical simplifications. And so the definition of what lexical simplification is, it's where you aim to reduce the lexical complexity or the word complexity of text whilst preserving the meaning of the text and the grammaticality. And there's many reasons why you might want to do this. One of the main reasons is that if you can automatically simplify the word content in text, then you can increase text accessibility for a wide range of different audiences. And we know, for instance, that a non-native speaker of English should know around 95% of the words within a piece of text to actually understand that text. So I'm going to talk at a high level now about what the steps are in order to perform lexical simplification, and then I'm going to talk about how our system specifically tackles these different steps. So the first one is complex word identification. And at this point, we really want to identify the words within the text that would be good candidates for substitution, so things that a reader might find difficult to understand. So in this example, I picked a word that's really hard to say, which wasn't good for the presentation, but he was annoyingly garrulous. Garrulous has been identified as a complex word here. So then the next step is substitute generation. So this is where you want to be able to create a set of valid substitutes that we could use to actually replace this particular complex word. So here we have two, talkative, chatty. And then the final step is we actually perform the simplification. So we take that complex word and replace it with the simpler alternative. So he was annoyingly talkative. So as I mentioned, this first step of complex word identification, we want to identify the words that a reader may find difficult to understand. And the way in which we do this is we start with a data set which has been collected specifically for complex word identification, collected by Yiman. And this data set contains annotations by 10 native and 10 non-native speakers of English. And they were presented with sentences from three different sources, so News, Wikinews, and Wikipedia sentences. And when they were presented with these sentences, they were asked to highlight which words within this sentence do you think that a learner of English would find difficult to understand. And this also included particular phrases as well. And around 35,000 words were annotated in total. So if we actually look at this example, we see that for the word flexed within the context of this sentence, 7 native speakers of English out of 10 have said, yes, this is a complex word, and 9 non-native out of 10. So there's quite high agreement here that flex within this context would be a word that's difficult to understand. And we take this data set and we train a sequential architecture, which is a recurrent neural network, to essentially predict, when I look at a sentence, is a word complex or not? And the reason that we use this architecture is it has a number of features that are very useful for the task of complex word identification. So the first one is that this architecture is bidirectional. And all we mean by that is that at the point that we train and predict whether a word is complex or not, we look at the whole of the left context of the word and the whole of the right context of the word. So we're really looking at this particular word within the context that it's being used to understand whether it's complex or not. And there are many examples within the data set where a particular word may have been marked as complex in one setting, but not necessarily in another. So we know that this is really important. The next thing that we consider are word and character level representations of the word. And again, this is really important because we know that particular morphology or particular character sequences within words can really impact whether they're seen as complex or not. And then finally, this model is trained with a joint objective of a language modeling objective. And all this means is that not only do we get the architecture to predict whether a word is complex or not, we also get the architecture to predict how likely is it that that word should occur within the particular context. And again, this is a really informative feature because we know for complex word identification that the likelihood of a word occurring, so essentially the frequency with which that word occurs, is closely correlated as to whether it's perceived as complex or not. Because, and that makes sense because the more frequent a word, the more likely you've had exposure to that word before. So once we've trained this architecture with our complex word data set, we can then apply it to sentences and see which words actually come out as complex. So for this sentence, when we apply, so this was the example that Katerina also showed, when we apply the classifier, these are the sort of words that come out as actually complex. And actually, yawning is a good example of a word that might not necessarily be complex, but because this has been used in a metaphorical context, it's picked up on the fact that that might be difficult. So once we've identified the words within the sentence that are complex, we order them from most likely to be complex word to least. And there's also a secondary step here where we remove any words that are proper nouns, because obviously they're very difficult to simplify. You can't really simplify like the name of a place. And then we lead into the next step. So we've identified the complex words. We take the most complex word, or the most likely to be complex word, and we then aim to create actual substitutes for this word. So traversed, within this context, we then create substitutes. And we use a range of traditional techniques to do that, as well as more contemporary techniques. So we actually have a couple of thesauruses. I actually did look at the plural can be thesauruses or thesauri before the presentation. But so yeah, we have a range of thesauruses. We have word embeddings, and essentially what that means is that we can look at, for all the different examples that traversed, for all the other words that have been used in a similar context to traverse, we can then use those as synonyms as well. And we create then a set of synonyms using all these different resources. And once we have this set, we then have to make sure that they're in the correct tense or the correct plurality as the original word, so that we know that when we put it back into the context, it will actually make sense. So once we have generated this set of synonyms, there are certain criteria that we have to actually narrow down by. And the first of these is the semantic fit. And what we mean by this is not necessarily all synonyms that you generate for a word are going to mean the same semantic, are going to have the same meaning when you put it back into the original sentence. And so we have to check, does this word actually mean the same as the original when we put it back in, to the sentence. The second is the grammaticality. So it's really important in text simplification that you're not introducing grammatical errors because it defeats the point. It's going to make the sentence not read well. And then finally, as this is textual simplification, we want the word that we replace the original with to actually be simpler than the word. So we check for simplicity. So with regards for the semantic fit, we use Elmo contextualized word representations. And all this is Elmo is a deep recurrent language model that has been trained on a vast amount of data, so actually 5.5 billion tokens of text. And this network can produce vectors for words which are completely dependent on the context that the word is being used in. So it's very good for polysemous words because it's all about the context of the word. So in this example, we can get a vector for each word within this sentence. And we can actually use these vectors, we can use the distance between these vectors as a way of measuring whether they're semantically similar within the context of the original sentence. So here's an example. This illustrates how sociologists, the start of a sentence, and illustrates has been identified as a complex word here. But when we actually look at the set of synonyms that are produced for this word, we see that there's two really distinct different groups. There's decorates, paints and draws, and there's also shows and exemplifies. And clearly within our context, we're looking for something like shows as opposed to decorates. So when we produce these vectors, we can produce a vector based on the context for illustrates, and we can produce one for decorates as well. And we can use the distance between these, so the cosine distance, to say, okay, how similar are these words within the context of the sentence? And we see here that we have a distance of 0.47, which relatively is quite a large distance and would say to the system, okay, this probably isn't a good semantic fit. Whereas if we compare the distance between shows, the vector for shows within the context of the sentence, with illustrates, we see that actually the distance is a lot closer, so now it's 0.06. So this is a really good way of being able to filter down whether these words actually mean the same within the context of our sentence. And we use two different measures for this. We use the whole context of the sentence, so essentially we create vectors using the whole sentence, and we also use a stripped down version, which is just the grammatical relations associated with that word, to get another measure of how similar the two words are. And we can then use a combination of both of these scores to say, okay, we don't think this is a good fit, or we do think that this is a good fit. So once we've filtered down according to whether this is a good semantic fit for the word or not, we then have to check if we substitute this word back into the sentence, will it make grammatical sense? And for this, we use a COCA corpus, which is over 560 million words. And more specifically, we look at the bigram frequencies of words within this really large corpus. And a bigram is literally two consecutive words. So children are would be a bigram, and are capable would be a bigram within this sentence. So when we generate synonyms for capable, one of the words that we get is able. And when you actually read children are able of, we know that that doesn't grammatically make sense. But the way that we can test this within the system is we look at the left bigram frequency. So are able, how many times does that actually occur within our 560 million word corpus? So we see here that it occurs a number of times, and that's fine. But when we actually look for able of, we see that there are no occurrences of this bigram within the whole 560 million words that we've looked at. And so this tells us one of two things. This either means that this isn't grammatical, and that's why it's never ever occurred, or it's extremely rare. And in either case, as this is simplification, it really implies to us that it's not a good choice to make. So once we've checked that it's semantically appropriate and we've checked that it should make grammatical sense as a substitution, we then have to check whether the word is actually simple. And to do this, we substitute the word back into the sentence and we run our original complex words labeler again and see, okay, are these words complex or not? And so then we perform our simplification step. So in this example, having checked all of the synonyms, narrowed them down, we make this substitution of traversed for crossed, and this is the complete lexical simplification for one word. And once we've done this, we then start completely again at the beginning of the pipeline, and we recheck the complexity of the words. And this is quite a key point, because we know that the very act of making a substitution within this text is going to change the perceived complexity of all the other words. So we do it in this stepwise way because the context really makes a massive difference on the overall perceived complexity. And we'll carry on performing these lexical simplifications until one of two things: either no further simplifications can be made, or a particular threshold has been reached. And the threshold could really be anything, but one thing that you might do is, as we said at the beginning, 95% of words should be known for a non-native speaker. So you could set the threshold so that once 95% of the words are simple, we'll stop simplification. And these are some of the simplifications that our system makes on this particular sentence. So you see hauled has been changed to carried, jagged has been changed to sharp, etc. And you'll notice that there are 3 words in blue that haven't been simplified. And this is because there are no appropriate synonyms to actually replace these words with. And that's okay, and sometimes that will happen. So to conclude, automatic lexical simplification allows us to adapt text to a wide variety of different readers, as well as not changing the meaning or grammaticality of that original text. And our simplification system achieves state-of-the-art on both complex word identification and end-to-end lexical simplification, and is currently in submission as a paper. And I'll leave at this example and ask if there are any questions. Thank you.
Thanks, Sian. Quick question about the COCA. 2 questions, actually. What thresholds do you use for the acceptance of bigrams? And why the COCA? Why not something like a larger 15 billion word N1010 or something corporate?
So I think in future work, we probably won't assess grammaticality in that way. The reason that we use COCA was because it was the only one available at the time that I could get free access to, in all honesty. But I mean, there are a variety of ways you can improve that, because you don't just have to look at the left and the right. You can look at like trigrams, you can look at wider context. I think, yeah, you could definitely use a larger corpus. I mean, Elmo is trained on 5.5 billion tokens, so of course, the more data, the better.
And your threshold, did you have a threshold cut off, or is it just
the threshold that we use is actually if there's no occurrence of it at all, because usually what happens is, whether they're grammatically correct or not, the step where you check how simple substitutes are tend to get rid of the ones that are very rare anyway. So we'll always pick the simplest semantic alternative, and usually they have like a very high frequency anyway, so there's no necessary need to cut off, because that simplification ordering will do that for you.
Hi, is the perception of complexity different based on the L1 of the learner? And if so, do you take that into consideration?
So I would say definitely. So we train 2 different models because, as I said, in our original complex word data set that we used to train the model, there's 10 native and 10 non-native. And we train 2 different models, well, 3. One that takes all into account, one just for native and one for non-native. We definitely see there's a difference between what native and non-native readers find difficult. And I definitely think that depending on L1, that will really change as well. Unfortunately, we don't have the data at the moment to be able to train a system to do that, but I think in future work that would be a really great idea to actually make it more specific, that identification of difficulty.
Thank you. I guess one of the ideas of Read and Improve is also for the learners to increase their vocab. So if you simplify all of the words, then obviously they wouldn't increase it. So is there some mechanism in there that allows them to be exposed to slightly more complex words than maybe they're used to, but so that they can still understand it?
Yeah, absolutely. So, as I said, there's a threshold. So we've incorporated it so that there's a threshold where we can say, okay, maybe we want 50% of the words to be simple and then 50% to be the same and not actually get simplified. So there's quite a few different ways you can actually adapt how you want the simplification to occur, because obviously it happens in a stepwise process anyway, so there's a lot of flexibility even in terms of, you saw the likelihood of complexity for words, and there is some sort of gradient that we see within the classifier that reflects these are very complex words, these are less complex words, and so we can even take it at like a level type basis.
Thank you.
Okay, hello. Are there any plans of taking also into account the, let's say, second language level, that like the CFR level, when you simplify? Because obviously, the target texts are targeted at specific levels. When you simplify, how does that change the target level in CFR terms, for example?
Well, we know that the original data set, when it was collected, had the background of the reader, whether they were advanced, intermediate or beginner. And if we could get access to those annotations, then we would be able to specifically have more of an idea of like what level we'd like to simplify for. And I think that that's future work that we're going to look at in the next month. But I mean, it's a good idea.
Yeah, that would be really, very, very useful in a second language environment. Yeah. Mix is essential. Yeah, definitely.